November 14, 1942, Republic Aviation Corporation, Farmingdale, Long Island. Alexander Kartveli stood in the assembly hangar, staring at a bolt that should not exist. The chief engineer of Republic Aviation held the fastener up to fluorescent light, turning it slowly, studying threading that was precisely wrong according to specifications. It was supposed to be grade 5 steel, heat-treated to 120,000 psi tensile strength. Instead, metallurgical analysis revealed grade 8, rated for 150,000 psi. Someone in the supply chain had substituted bolts. A mistake, a deviation from approved engineering drawings, the kind of error that should trigger immediate correction. Kartveli's assistant, James Wright, waited for the inevitable order. Replace them all. But Kartveli remained silent, mind racing through implications. The P-47 Thunderbolt was already the heaviest single-engine fighter in production, 8 tons fully loaded, powered by a massive Pratt & Whitney R2800 double wasp engine, producing 2,000 horsepower, designed to dive faster than any aircraft in existence. And now, by accident, its wing spars were reinforced with bolts, 30% stronger than specification. Kartveli looked at Wright and said something unexpected. "Don't replace them. I want to test what happens when we build a fighter that's over-engineered by mistake." That accidental decision would save thousands of pilots' lives and redefine what combat aircraft could survive. The P-47 Thunderbolt emerged from unusual requirements. In 1940, the U.S. Army Air Corps demanded a fighter capable of escorting bombers deep into enemy territory at altitudes above 30,000 feet, higher than any existing fighter could effectively operate. It needed range, firepower, and survivability. Alexander Kartveli, Russian-born engineer who had fled the Bolshevik Revolution, approached the problem with obsessive attention to structural integrity. He had witnessed too many aircraft disintegrate during his career. His design philosophy was simple: build it strong enough to withstand forces beyond any pilot's physical limits. The P-47 design was radical. Where contemporary fighters like the Spitfire and Bf-109 weighed around 6,000 pounds, Kartveli's monster weighed 13,000 pounds empty, nearly 18,000 pounds combat-loaded. Critics called it the flying milk bottle, the jug, the 7-ton shit hauler. They claimed it was too heavy, too large, too slow in climb rate. Kartveli ignored them. He knew something others didn't. Mass, properly distributed, was armor. Weight meant structure. Structure meant survival. The wing design was particularly crucial. Kartveli specified semi-monocoque construction with main spar running full span, supported by secondary spars and stringers. The spar was aluminum alloy, but connection points, where wings attached to fuselage, used steel bolts because those joints absorbed maximum stress during high-G maneuvers. Engineering specifications called for SAE grade 5 bolts, 120,000 psi tensile strength, sufficient for calculated maximum loads of 8G positive, 4G negative. But in October 1942, Republic Aviation's supply department received delivery of 50,000 bolts from subcontractor in Pennsylvania. The bolts looked identical to specified parts. Same dimensions, same threading, same finish. They were installed in 43 P-47s before quality inspector named Thomas Chen randomly tested one bolt and discovered the discrepancy. Grade 8 instead of grade 5, 30% stronger. Chen immediately flagged the issue. Standard procedure required removing all wrong bolts, scrapping affected aircraft if necessary, and investigating how the error occurred. That's when Kartveli made his unusual decision. Instead of treating it as catastrophic error, he saw it as accidental experiment. What if the P-47 could withstand even greater forces than designed? What if over-engineering the most critical structural component actually unlocked capabilities they hadn't anticipated? He ordered the wrong bolts to remain installed in those 43 aircraft, but marked them specially for intensive testing. And he requested permission from Army Air Corps to conduct extreme stress testing, diving those P-47s beyond their official limitations to see what would break. Or, more precisely, to see what wouldn't. The Army Air Corps Test Division at Wright Field, Ohio, was skeptical. Major Donald Blakesley, chief test pilot, reviewed Kartveli's proposal with visible incredulity. "You want me to intentionally dive a fighter past its rated speed, past its certified G limits using bolts that aren't even correct specification, to see if it breaks?" Kartveli nodded. "Not to see if it breaks. to see how much it can withstand before it breaks. Blakesley studied the engineer. And if it disintegrates at 500 miles per hour with me inside? Cartveli smiled thinly. Then we will know the limit. Science requires data. Sometimes data requires risk. Blakesley accepted, not because he was reckless, though he was certainly fearless, but because he understood something fundamental about engineering progress. Theoretical calculations only go so far. Real-world testing reveals truths that equations cannot predict. On November 28, 1942, Blakesley climbed into P-47B serial number 416065, one of the aircraft with the wrong bolts. The test protocol was simple but terrifying. Climb to 35,000 feet, roll inverted, pull into vertical dive, accelerate to maximum speed, pull out at lowest safe altitude. The dive began at 09:47 hours. Blakesley rolled the massive fighter and pushed the stick forward. The P-47 dropped like a steel meteor. Airspeed indicator climbed, 300 mph, 400 mph, 450 mph. The aircraft began vibrating. At 480 mph, the vibration intensified to violent shaking. Standard dive limitation was 475 mph, indicated airspeed. Blakesley pushed past it, 500 mph, 520 mph. The wings flexed visibly, bending upward by nearly 3 feet at the tips. The fuselage groaned. Rivets screamed, but nothing failed. At 8,000 feet, Blakesley initiated pullout. He hauled back on the stick with both hands, straining against G-forces that crushed him into his seat. His vision tunneled. Blood drained from his brain toward his legs. The G-meter pegged at 11 G, nearly 3 times the aircraft's official limitation. His consciousness flickered, but the P-47 held together. Wings bent but didn't break. Fuselage twisted but didn't crack. The wrong bolts, 30% stronger than specification, absorbed forces that would have sheared standard bolts. Blakesley leveled at 2,000 feet, hands trembling, body aching from G-induced trauma. He keyed radio transmitter. Right tower, 416065. Test complete. Aircraft is intact. Jesus Christ, this thing is built like a tank. In the control tower, Cartveli allowed himself rare smile. His accidental over-engineering had just proven something extraordinary. The P-47 could withstand punishment beyond anything contemporary fighters could survive, and they had barely begun to explore its limits. Over the next 6 weeks, test pilots pushed P-47s with the reinforced bolts through increasingly extreme scenarios. They dove from 40,000 feet, reaching speeds exceeding 550 mph, approaching the sound barrier's edge where compressibility effects began destroying aircraft. They pulled out at G-forces that should have ripped wings off. They performed maneuvers explicitly forbidden by flight manuals. Snap rolls at maximum speed, inverted dives, terminal velocity recoveries at treetop altitude. The P-47s absorbed it all. But one test revealed something unexpected. Captain Harold Comstock, testing aircraft 416072, entered high-speed dive and encountered phenomenon that would later be understood as transonic shock waves. At 525 mph, indicated airspeed. Airflow over parts of the wing exceeded local speed of sound. Shockwaves formed, causing violent buffeting and loss of control authority. The aircraft pitched downward uncontrollably. Comstock fought the stick, but the P-47 continued accelerating in near vertical dive. Traditional recovery was impossible. Pulling back only increased angle of attack, worsening the shockwave formation. Comstock made split-second decision. Instead of fighting the dive, he rolled the aircraft inverted, used rudder to yaw the nose sideways, breaking the shockwave pattern. The buffeting ceased. He rolled upright and pulled out successfully, but only after diving to 800 feet above ground. Post-flight inspection revealed something astonishing. The wing spar bolts had absorbed and distributed forces that deformed the surrounding aluminum structure. The metal around the bolts showed permanent compression, meaning the bolts had been stressed beyond elastic limit. Standard grade 5 bolts would have sheared completely, resulting in catastrophic wing failure. The grade 8 bolts survived, though barely. Cartveli examined the damage with reverence. "Look at this," he told his engineering team, pointing to deformed metal. The bolts held when everything around them wanted to fail. They became the foundation that kept structure together even when other components began yielding. It was revelation. Over-engineering critical points didn't just add safety margin. It created failure hierarchy. a system where less critical components could deform or break, while essential structural elements remained intact, allowing pilot to maintain control and potentially save aircraft. This understanding transformed Republic Aviation's design philosophy. Kartveli immediately ordered all P-47 production shifted to grade 8 bolts as standard specification, but he went further. He systematically identified every critical structural connection point and upgraded fasteners beyond minimum requirements. The wrong bolt had taught him that in combat aviation there was no such thing as too strong, only strong enough to save lives or not strong enough. He chose the former permanently. The decision to standardize over-engineered fasteners had immediate cost implications. Grade 8 bolts cost 40% more than grade 5. With each P-47 requiring approximately 8,000 fasteners in various sizes, the price increase per aircraft was substantial. Republic Aviation's comptroller, Edward Morrison, calculated that upgrading all fasteners would add $200 per aircraft, equivalent to roughly $20,000 in 2025 dollars. Multiplied across projected production of 15,000 P-47s, that represented $18 million additional cost. Morrison presented these figures to Republic's Board of Directors in January 1943. Gentlemen, we're discussing spending $18 million to solve a problem that doesn't officially exist. The original specifications were adequate. This upgrade is unnecessary. Kartveli, present at the meeting, responded with controlled intensity. Mr. Morrison, you are correct that the original specifications met calculated requirements. But calculations don't account for the chaos of combat. Pilots will push these aircraft beyond any limitation we specify. They will dive to escape, pull maximum G to evade, absorb battle damage, and still fly home. The difference between grade 5 and grade 8 bolts is the difference between structural failure at 9G and structural integrity at 12G. That margin will save lives. How do you calculate the value of a pilot's life? The board approved the expenditure, but Morrison's concerns were not entirely unfounded. Military procurement officers questioned why Republic was unilaterally upgrading specifications and increasing costs. Lieutenant Colonel Benjamin Kelsey, chief of fighter projects at Wright Field, demanded explanation. Kartveli provided it in characteristically blunt terms. Colonel, we accidentally discovered that our aircraft can survive forces that would destroy any other fighter in existence. We can either keep that capability secret and revert to cheaper components, or we can make it standard and give every pilot the best chance of survival. I choose survival. Kelsey, himself an experienced test pilot, understood immediately. He authorized the specification change and went further. He recommended similar upgrades for other aircraft types, but most other manufacturers rejected the approach, considering it unnecessarily expensive. Lockheed's P-38 Lightning, Bell's P-39 Airacobra, North American's P-51 Mustang, all continued using minimum specification fasteners to control costs and weight. This divergence would have profound consequences when these aircraft entered combat. The P-47's structural over-engineering, born from accidental bolt substitution, would become its defining characteristic. Pilots would discover they could subject Thunderbolts to abuse that would destroy lighter fighters. They could dive away from danger at speeds others couldn't match. They could survive hits that would doom sleeker aircraft. The wrong bolt had become the right choice, and that choice was about to be tested in the crucible of actual warfare. The first P-47s reached England in December 1942, assigned to the 56th Fighter Group based at Horsham St. Faith. American pilots trained in lighter aircraft initially despised the massive fighter. Captain Gerald Johnson wrote to his family, "They've given us flying refrigerators. This thing climbs like a brick and turns like a freight train. I'd give anything to be flying a Spitfire instead." The British were even more dismissive. RAF pilots called it the American steamroller and doubted it could survive against experienced Luftwaffe pilots in nimble Bf-109s and FW-190s. The first major combat test occurred on April 15, 1943, during bomber escort mission over occupied France. 48 P-47s from the 56th and 78th Fighter Groups escorted B-17s attacking rail yards near Paris. At 28,000 feet, 30 Focke-Wulf 190s attacked from above, the Luftwaffe's preferred tactic, diving with speed and altitude advantage. The German fighters were faster in level flight, more maneuverable, and their pilots were veterans with hundreds of combat hours. But the FW-190 pilots expected American fighters to react like Spitfires, turn to meet the attack, engage in turning dogfight. The P-47s did something different. Instead of turning, they dove, straight down, using gravity and their massive weight to accelerate beyond anything the FW-190s could match. Lieutenant Robert Johnson, flying P-47C serial 416235, pushed his aircraft into near-vertical dive, airspeed exceeding 500 mph. Two FW-190s followed but couldn't keep pace. At 15,000 feet, Johnson pulled out, 11G pullout that compressed his spine and temporarily grayed his vision. The FW-190s, limited to 8G maximum, couldn't match the maneuver. They had to ease their pullouts or risk structural failure. Johnson reversed, climbed back toward the German fighters who were still recovering from their own dives. Now he had altitude and speed advantage. He lined up on a FW-190, fired a 2-second burst from 850 caliber machine guns, 400 rounds of armor-piercing and incendiary ammunition, and the German fighter exploded. First confirmed kill for the P-47 in European theater. Other pilots discovered the same tactic independently during the same mission. The P-47's weight and structural strength allowed dive and zoom tactics impossible for lighter fighters. German pilots reported confusion. The American fighters don't fight like fighters. They fight like dive bombers that shoot back. It was accurate description. The P-47 wasn't trying to turn with opponents. It was using energy fighting, converting altitude to speed, speed to killing position, then climbing to regain altitude. The over-engineered wing spars that allowed extreme G-forces made this tactic survivable. Without those wrong bolts, the wings would have failed during those violent pullouts. As P-47s accumulated combat hours, pilots discovered the aircraft could absorb damage that would doom other fighters. On June 26, 1943, Lieutenant Robert Johnson, same pilot from April encounter, experienced this dramatically. Escorting bombers over Pas-de-Calais, his P-47 was attacked by FW-190, flown by German ace Egon Meyer. Johnson didn't see the attack until 20mm cannon shells shredded his aircraft. Shells destroyed the canopy, shattered his windscreen, severed control cables, punctured fuel tanks, and wounded Johnson in multiple places. His P-47 should have disintegrated. The damage was catastrophic. But the aircraft continued flying. Johnson, bleeding and partially blind from glass fragments, managed to maintain control using only trim tabs and throttle. He couldn't bail out. His canopy was jammed. He couldn't fight. His guns were inoperable. He could only fly. And the P-47, despite missing large sections of fuselage skin, continued responding to inputs. Meyer pursued, firing repeatedly. More shells hit. Johnson's aircraft was transformed into flying scrap metal. Meyer expended all ammunition trying to finish him. Finally, out of options, the German pilot pulled alongside, saluted, a gesture of respect for opponent who simply wouldn't die, and broke off. Johnson nursed his destroyed P-47 across the English Channel, landed at the first available airfield and collapsed. Post-flight inspection counted over 200 holes in the aircraft. The wing spar was intact. The over-engineered connection points held. Engineers calculated that lighter fasteners would have sheared under the combined stress of battle damage and violent evasive maneuvers. Johnson had survived because of bolts installed wrong 8 months earlier. Word of P-47 survivability spread through American fighter groups. Pilots who initially hated the aircraft began appreciating its virtues. Yes, it was heavy. Yes, it climbed slowly. Yes, it couldn't turn with Bf-109s, but it brought them home. Colonel Hubert Zemke, commander of the 56th Fighter Group, wrote in Operations Report, "The P-47 is not a fighter in traditional sense. It's a weapon system designed around pilot survival. It trades maneuverability for structural integrity. In extended campaign, keeping pilots alive matters more than dogfighting performance. Experienced pilot in durable aircraft beats inexperienced pilot in nimble aircraft." This philosophy proved correct. P-47 units suffered lower loss rates than P-38 or early P-51 units despite facing same opposition. The difference wasn't pilot skill. It was aircraft that could withstand mistakes, survive hits, and bring damaged aircraft home. The wrong bolt had created right aircraft for brutal attrition warfare over Europe, and combat losses were about to prove this decisively. By summer 1944, P-47s were operating throughout all theaters: Europe, Mediterranean, Pacific, China, Burma, India. Each environment tested the aircraft differently. In Europe, battles occurred at high altitude, 25,000 to 35,000 feet, where thin air meant less aerodynamic stress, but extreme cold threatened mechanical systems. In the Pacific, combat was low altitude, under 15,000 feet, where tropical heat, humidity, and corrosive salt air degraded materials. The P-47 excelled in both extremes because its over-engineered structure provided margin for environmental stresses beyond combat damage. In the Pacific theater, the 348th Fighter Group discovered unexpected advantage. Japanese fighters, Zeros, Oscars, Tonys, were designed for maneuverability and climb rate, sacrificing structural strength and armor. They could outturn P-47s effortlessly, but American pilots employed tactic called boom and zoom. Dive from altitude, fire during high-speed pass, climb away before Japanese fighters could react. The tactic required aircraft capable of surviving 10 G+ maneuvers repeatedly, multiple times per sortie, in tropical heat that reduced structural margins. Major William Dunham, commanding 460th Fighter Squadron, documented this in Mission Report from Leyte, Philippines, November 1944. Engaged 12 Oscars at 18,000 feet. Dove to 400 mph indicated, fired on leader, climbed back to altitude, repeated sequence 6 times in 15 minutes. Aircraft experienced estimated 911 G loads on each pullout. Temperature 95 degrees, humidity extreme. Post-flight inspection revealed no structural damage. Maintenance officer reported wing spar bolts showed no deformation. Aircraft ready for next mission. This was extraordinary. 6 high-G maneuvers in tropical heat and the structure remained sound. Contrast this with P-38 Lightning experience. The P-38, lighter and more maneuverable than P-47, suffered chronic structural problems in Pacific theater. Its twin-boom design concentrated stress differently, and standard fasteners failed under repeated high-G loads in hot conditions. Multiple P-38s experienced catastrophic wing failures during combat maneuvers. Investigation revealed fastener fatigue. The bolts met specifications but couldn't withstand cumulative stress of tropical operations plus combat loads. Republic Aviation received these reports and vindicated Cartveli's decision. The additional cost of over-engineered fasteners was saving lives across multiple theaters. Army Air Forces headquarters issued study in January 1945 comparing loss rates. P-47 units suffered 1.2 aircraft losses per 100 sorties. P-38 units, 2.1 per 100. P-51 units, 1.8 per 100. Some difference was operational factors, types of missions, opposition faced, but structural survivability was significant contributor. P-47s came home damaged. Other fighters didn't come home at all. The wrong bolt had become industry standard, but its most dramatic vindication was still to come, in skies over Germany where Luftwaffe pilots would discover that even direct hits couldn't bring down the American Jug. March 1945. The air war over Germany had reached maximum intensity. Luftwaffe, though diminished in numbers, fielded experienced pilots in advanced aircraft, FW-190D9, Dora, and Me-262 jet fighters. These aircraft outperformed P-47s in nearly every metric. The Dora was faster in level flight. The Me-262 was faster in all regimes. Both could outclimb the Thunderbolt. By conventional analysis, P-47s should have been outclassed. But combat doesn't follow conventional analysis. Lieutenant Colonel Francis Gabreski, leading ace of the 56th Fighter Group with 28 confirmed kills, encountered Me-262 on March 3, 1945, near Berlin. The jet attacked his flight from above, standard tactic for speed advantage. Gabreski's wingman was hit immediately. 20mm cannon shells shredded the P-47's tail, but the aircraft remained controllable. The pilot managed emergency landing in Allied territory. The Me-262 reversed for second pass. Gabreski knew he couldn't outrun or outmaneuver a jet, but he could outdive it. He pushed into vertical dive, accelerating to 550 mph indicated, approaching compressibility limits. The Me-262 followed but couldn't match the dive angle. Jet engines of 1945 were temperamental. Extreme maneuvers caused flameouts. The German pilot eased his dive, losing pursuit angle. Gabreski pulled out at 3,000 feet, experiencing crushing 12G load that caused temporary blackout. His vision returned to find the Me-262 overshooting high and fast. Gabreski reversed, climbed, and managed snapshot as the jet tried to disengage. He missed, But the encounter proved something. Even Germany's most advanced fighter couldn't force P-47 into unfavorable engagement if the American pilot exploited structural advantages. Post-war interrogation of Luftwaffe pilots revealed their frustration. Major Walter Krupinski, Me-262 pilot with 197 total kills, stated, "The P-47 was not our most dangerous opponent in terms of performance, but it was our most frustrating. You could hit them repeatedly, and they kept flying. You could outmaneuver them, but they would dive away before you could finish them. And if you made one mistake, one moment of inattention, their 8 machine guns would destroy you instantly. It was aircraft designed not to win dogfights, but to survive them. In war of attrition, survival matters more than elegance." This was unintentional compliment. Kartveli hadn't designed the P-47 to be elegant. He designed it to be unbreakable. The wrong bolt was physical manifestation of that philosophy. Overpowered, overweight, over-engineered. Not optimal by any single metric except the one that ultimately mattered, bringing pilots home alive. The war ended in August 1945. Final tally, 15,786 P-47 Thunderbolts produced. They flew 546,000 combat sorties, destroyed 11,874 enemy aircraft, 9,000 locomotives, 86,000 railroad cars, 68,000 trucks, and dropped 132,000 tons of bombs. But the statistic that mattered most to pilots: the P-47 had the lowest loss rate per sortie of any American fighter in European theater. Where other fighters were lost at rates exceeding 2%, P-47s were lost at 1.2%, a difference representing thousands of pilots who survived the war. After victory, military analysts studied why. Tactical reports, engineering assessments, pilot testimonies were compiled into comprehensive analysis. The findings validated Kartveli's accident-driven over-engineering. The P-47's structural strength allowed tactics impossible for other fighters: extreme dive speeds, violent high-G maneuvers, ability to absorb battle damage, and continue fighting. These capabilities traced directly to overbuilt structure, and that structure traced to stronger fasteners, and those fasteners traced to supply chain error in October 1942. But history rarely unfolds linearly. Republic Aviation's archives revealed something unexpected. Kartveli had been deliberately lobbying suppliers for stronger fasteners months before the accidental substitution. He believed specifications were inadequate but couldn't convince Army Air Corps procurement to authorize more expensive components. The wrong bolt delivery gave him opportunity to prove his theory through testing rather than argument. The accident provided political cover for decision he wanted to make anyway. In 1950 interview, Kartveli admitted this. "Did I know the bolts were wrong when they arrived? Yes. Did I order immediate replacement? No. Did I claim it was fortuitous accident to avoid procurement battles? Perhaps. But I knew in my bones, that fighter aircraft must be overbuilt. I learned this from watching aircraft fail in Russia, in Europe, in early American tests. Pilots die when engineers cut margins too thin. The wrong bolt was not wrong. It was correct all along. We were wrong to specify weaker components. This revelation complicated the narrative. It wasn't pure accident. It was engineered serendipity, experienced engineer recognizing opportunity when mistake aligned with his convictions. But whether accident or orchestrated event, the result was identical. Thousands of pilots owed their lives to bolts 30% stronger than officially required. And that engineering decision would influence aircraft design for decades. Post-war fighters inherited P-47's philosophy. The F-86 Sabre, F-100 Super Sabre, F-4 Phantom, all emphasized structural strength over minimum weight. All over-engineered critical components. All traced lineage to the lesson learned when wrong bolt made fighter unbreakable. Sometimes the mistake is discovering we were wrong about what was right all along. Alexander Kartveli continued designing aircraft until his retirement in 1960. His subsequent designs, the F-84 Thunderjet, F-105 Thunderchief, carried forward the over-engineering philosophy. Both aircraft were criticized as overweight, but both achieved exceptional survivability records. The F-105, though suffering high losses in Vietnam due to surface-to-air missiles, had extraordinarily low loss rate from structural failure. Pilots nicknamed it Thud, short for Thunderchief, but also because it could absorb punishment that would destroy lighter aircraft and still thud onto runways safely. But Kartveli's obsession with structural integrity had costs. His designs were always heavier than competitors. They required more powerful engines, consumed more fuel, cost more to produce. In peacetime procurement battles where performance specifications and cost-dominated decisions, Kartvel's philosophy often lost. His F-103 proposal, a fighter designed to survive nuclear blast shockwaves, was rejected as too heavy and expensive. His XF-91 Thunderceptor, designed with inverse taper wings for extreme high-altitude performance, lost to the F-104 Starfighter, despite superior structural strength. The F-104 comparison is instructive. Lockheed's design philosophy was opposite of Kartvel's: minimize weight, maximize performance, accept reduced safety margins. The F-104 was sleek, fast, and dangerous. It suffered catastrophic accident rate. 30% of German Luftwaffe F-104s were lost in crashes. Structural failures were common: wings folding during high-G maneuvers, fuselage breaking during hard landings. German pilots called it Witwenmacher, widowmaker, but it won procurement contracts because it looked impressive in specification sheets. This frustrated Kartveli deeply. In 1958 interview with Aviation Week, he said, "We design aircraft as if pilots are expendable resources. We optimize for performance metrics that look good on paper but kill men in real operations." The P-47 taught us that overbuilt aircraft save lives, but we forget lessons as soon as war ends. We return to minimizing costs and maximizing speed. Then war returns, and we relearn expensively with pilots' lives what we should have remembered. He was prophetic. Vietnam War exposed multiple aircraft with inadequate structural margins. The F-4 Phantom, though eventually successful, suffered early losses from wing spar failures during hard maneuvering. The F-111 experienced catastrophic wing pivot failures. Modifications required billions of dollars and years of groundings. Engineers reinforced structures, upgraded fasteners, added safety margins, exactly what Kartveli had advocated decades earlier. The wrong bolt lesson was forgotten and relearned at tremendous cost. And Kartveli, watching from retirement, must have felt vindication mixed with tragedy. He had shown the way. But institutional memory is short, and peacetime procurement favors appearance over survival. The cycle repeats: under-design, failure, retrofit, relearn, until the next war demands the truth that Bolt taught us. There is no such thing as over-engineered when lives depend on structure holding together. Alexander Kartveli died in 1974 at age 76. His obituary in the New York Times mentioned his role designing the P-47 but didn't mention the Bolt. That detail remained buried in Republic Aviation's engineering archives, known only to specialists. For decades, the story of how accident improved America's most successful fighter was footnote in technical histories, unknown to general public. Rediscovery came in 1995, when aerospace historian Warren Bodie researched his comprehensive P-47 history. Republic's P-47 Thunderbolt, From Seversky to Victory. Bodie interviewed surviving Republic aviation engineers, reviewed archived correspondence, and found internal memos documenting the bolt substitution and Kartveli's decision to retain stronger fasteners. Bodie recognized the significance. It wasn't just trivia about manufacturing error, but fundamental insight about engineering philosophy and how accidents sometimes reveal truths more profound than planning. Bodie's revelation sparked reassessment of engineering practices across aerospace industry. Modern aircraft engineers working on F-22 Raptors and F-35 Lightning IIs studied the P-47 case as lesson in safety margins and structural redundancy. Computer modeling could predict failure modes with precision impossible in 1940s, but the core principle remained. Critical components should exceed calculated requirements because real-world stresses always exceed models. The Bolt's legacy extends beyond aviation. Structural engineers in other fields, bridge design, skyscraper construction, spacecraft development, cite P-47 case study when advocating conservative safety factors. The Challenger space shuttle disaster in 1986 was partly caused by O-rings specified to minimum requirements with inadequate safety margin. Post-accident investigation cited examples like the P-47 Bolt, instances where over-engineering saved lives by providing margin for unexpected stresses. In 2009, Smithsonian Air and Space Museum restored P-47D-40RA, serial number 45-49295, for permanent display. During restoration, engineers examined original wing spar bolts, Grade 8 fasteners installed in 1945. After 64 years, including thousands of flight hours during war and decades of static display loads, metallurgical analysis showed the bolts retained 94% of original strength. Standard grade 5 bolts would have shown significantly more fatigue and degradation. The curator, Dr. Robert van der Linden, noted, "This single component represents larger truth about engineering. The difference between adequate and excellent is often invisible until stress reveals it. These bolts look identical to weaker versions. But under load, combat, damage, extreme maneuvering, they meant life or death." The museum display includes placard explaining the bolt story, its small note beneath massive aircraft. But visitors who read it often pause longer than at other exhibits, because it's a reminder that sometimes our mistakes reveal what we should have done intentionally, and sometimes accident teaches lesson more valuable than any deliberate plan. Build it stronger than necessary, because necessity often exceeds expectations. But the true climax of this story isn't in combat victories or engineering vindication. It's in the quiet moment when pilot realizes his aircraft saved his life, and that salvation traces to decision made by engineer who never flew in combat, working from problem created by supply clerk who never intended heroism. It's recognition that survival often depends on invisible margins engineered by people we'll never meet, solving problems we'll never consciously face. Lieutenant Robert Johnson, the pilot who survived Egon Mayer's attack in June 1943, lived until 1998. In his final interview before death, he was asked what he remembered most about the war. He didn't mention his 7 confirmed kills, or his Distinguished Service Cross, or his survival of that devastating attack. Instead, he said, "I remember touching the wing of my P-47 after that mission, just putting my hand on the metal, feeling how solid it was, how it held together when everything should have fallen apart. Someone built that aircraft, someone I never met, and they built it strong enough to save me. I think about that person sometimes. Maybe they were engineer, or assembly worker, or inspector who checked bolts. They did their job well enough that I got to live another 55 years, marry, have children, see grandchildren. They gave me a life, and they probably never knew. That's the real story of the wrong bolt. Not that it made the P-47 fly faster or fight better, but that it created margin between life and death. Margin exploited thousands of times by pilots in desperate circumstances. Margin engineered intentionally accidentally by Cartveli, approved by military officers who trusted his judgment, manufactured by workers who probably never saw combat, installed by mechanics who never flew fighters. Warfare is violent chaos where plans fail and randomness dominates. But within that chaos, engineering creates pockets of reliability. Structure that holds when everything else fails. Metal that doesn't break when stressed beyond specification. Bolts that grip when forces try to tear wings off. These aren't glamorous. They don't appear in combat reports or victory counts. But they're difference between pilot returning to base or dying in fireball over enemy territory. The P-47's unbreakable dive capability, born from bolt installed wrong, represents something deeper than engineering accident. It represents philosophy. Build for survival first, performance second. Accept weight penalty for structural margin. Spend money on components that might never be stressed to limits. Because when they are stressed, lives depend on them absolutely. That philosophy saved thousands. And we forget it at our peril every time we optimize for efficiency over resilience. The P-47 Thunderbolt flew its last combat mission in 1955 during the Suez Crisis, flown by French forces. By then, it was obsolete, superseded by jets that flew higher, faster, and more efficiently. But even in obsolescence, the P-47 maintained its reputation. Pilots trusted it absolutely. When French pilots were offered choice between aging P-47s and newer but less proven aircraft, many chose the Thunderbolt. "I know it will bring me home," one pilot explained. That trust, earned over thousands of combat missions, traced ultimately to engineers' decision to keep wrong bolt. The story could be dismissed as historical curiosity, interesting anecdote about World War II aircraft. But it's more than that. It's case study in how small decisions cascade into large consequences. A supply clerk ships wrong bolts. An engineer recognizes opportunity rather than error. A test pilot survives dive that should have killed him. A procurement officer approves cost increase. Thousands of pilots exploit structural margin in combat. Most return home. Some of them have children who live today because thread on bolt was cut slightly deeper, heat treatment slightly longer, steel alloy slightly stronger. We live in a world where engineering decisions accumulate invisibly into infrastructure of survival. Buildings stand through earthquakes because engineers specified concrete stronger than minimum code. Bridges carry traffic through storms because structural elements exceed calculated loads. Aircraft fly through turbulence because components tolerate stresses beyond normal operations. These margins are expensive. They add cost to every project. And in peacetime, when catastrophe is abstract future possibility rather than immediate threat, there's constant pressure to minimize those margins. The P-47 bolt reminds us, margins matter. Over-engineering saves lives. The difference between adequate and excellent is invisible until moment of maximum stress, and then its difference between survival and catastrophe. Alexander Kartveli understood this instinctively. His wrong bolt was right, because it admitted truth that specifications often ignore. We don't know maximum stress until we experience it, so we should build for stresses beyond imagination. Today, when engineers design aircraft or buildings or bridges, some reference the P-47 case. They advocate for margins that seem excessive. They fight against cost-cutting that eliminates redundancy. They're protecting future users from stresses those users don't yet know they'll face, because that's what engineering is, building structure that holds when everything else fails. The wrong bolt held. Thousands of pilots lived. And the lesson endures. Sometimes the mistake is assuming minimum requirements are sufficient. Sometimes strength that seems excessive is exactly enough.